Data Skeptic is the official podcast of dataskeptic.com, bringing you stories, interviews, and mini episodes on topics in data science, machine learning, statistics, and artificial intelligence.
Michael Kearns is a professor and the National Center Chair at the Computer and Information Science Department at the University of Pennsylvania. He holds a secondary appointment in the Department of Economics, with joint appointments in the Wharton School's Department of Statistics and Department of Operations, Information, and Decisions. Michael is also the founding director of the Warren Center for Technology and Data Sciences and the founding co-director of Penn's Engineering's Networked and Social Systems Engineering program. In addition, he is chief scientist of Mana Partners, a trading, technology, and asset management firm. Michael holds a PhD in computer science from Harvard University. His research interests include topics in machine learning, algorithmic game theory and microeconomics, computational social science, and quantitative finance and algorithmic trading. Michael, welcome to Data Skeptic.
Thank you for having me.
It's a real pleasure. I'm glad we got a chance to speak for a number of reasons because I think there's a couple interesting things we can touch on. But in particular, I would say that you did a lot of foundational work applying complexity theory to machine learning. So maybe to open up, I'm curious how you developed an interest in the overlap of these two areas.
Well, I guess I knew even as an undergraduate that I was quite interested in theoretical computer science and complexity theory and, kind of the design of algorithms, but wasn't really that interested in applying that to very traditional computational problems. And so I was particularly interested in, applications of complexity theory outside of core computer science problems. When I was applying for grad school as an undergraduate, I became aware of the very early works by my eventual advisor, Les Valiant at Harvard, trying to apply complexity theory and the analysis of algorithms to learning in general, not in particularly machine learning. This was, well before machine learning was a thing, so to speak. Mm-hmm. And I just found that whole framework very exciting and appealing and a great mixture of kind of the mathematical with natural phenomena, in this case, learning.
When I started learning the basics of complexity theory, let's just say come up with the runtime of something like Dijkstra's algorithm. I don't want to trivialize what an achievement it was that Dijkstra figured that out, but it sort of is a straightforward thing. The algorithm's pretty deterministic. Yet when we look at machine learning algorithms, they're almost like meta-algorithms in some sense. They're a process that's going to look at some data and build some model, and it's going to behave presumably very differently under different inputs. Does that mean we need new analytical tools, or is it just the same thing, a little bit more tricky to figure out anything complexity-wise?
Well, I think it's a bit of both. Most learning problems or formulations actually do have a pure optimization piece underlying them, much like Dijkstra's algorithm does. Instead of the input being a network or a graph, the input is a data set, and your goal is to search some very large space of possible solutions, which in this case are predictive models. And so there is quite a bit of overlap with just good old-fashioned traditional analysis of algorithms with the analysis of machine learning algorithms from a complexity theoretic viewpoint. I think where things depart is that, with something like Dijkstra's algorithm, the optimization itself is the end goal. You want to find the shortest paths in the network. Whereas in the case of learning, you're only optimizing on the data set in front of you in the hopes that it'll generalize out of sample. And so there's kind of this statistical or even induction piece that's missing in something like Dijkstra's algorithm. And so there are these very interesting connections, as you and maybe your listeners have heard in other versions of your show, between, just the pure optimization piece on the data in front of you and what you can say out of sample on new data. That's where things get interesting and where you have to take account of kind of how complex the models you're building are.
There's also some neat things now to consider in terms of the size of the training set we have. What's learnable given some bounded input. And I guess that's sort of somewhat unique to machine learning. Can you talk a little bit about the strategies for determining, the complexity bounds on sample versus algorithms?
There are very mature and refined theories and algorithms for balancing the goodness of fit you can get on a data set with how well you'll do out of sample on new data drawn from the same distribution process or what have you. And one of the interesting things about machine learning is the close interplay between that and algorithmic issues. And this kind of continues on to this day in the form of deep learning and related topics. Overall, I mean, I think probably all of your listeners can appreciate the fact that if you give me any two data points, I can fit a straight line to them, but none of us would have any confidence that the third point that came in would fall on that same line. And it's not a stretch. Doesn't stretch the truth to say that that example is kind of at the crux of the more general problem of balancing the fact that if you give me a data set, I can always model or fit it perfectly if you give me a complicated enough model, but it's like the line fit to two data points. And so, one big area of machine learning and the analysis of learning algorithms in general is the topic known as complexity regularization, which is how exactly should I measure goodness of fit, and how should I measure the complexity of my model, and how should I balance those two, and how can I do that in a scalable, efficient way algorithmically. And it's an interesting area because there's a lot of interplay between algorithms and statistics, if you like, and probability theory.
Would you mind giving a definition of P-concepts or probabilistic concepts and how they're a useful abstraction in doing this sort of analysis?
Yeah, I'm not sure I think of that as a directly related topic, and you probably got that from one of my ancient papers. I doubt anybody would call it P-concepts anymore. But the idea of a probabilistic concept, if you think about a model that makes binary predictions, like it's going to rain today or it's not going to rain today, the idea behind a probabilistic concept is to make a more sensible probabilistic prediction, like it's going to rain today with 40% probability. One topic that has a very old history in this area, that predates machine learning as a field, it goes back to statistics, is just how you should reward or punish such predictions in a way that, if you like, incentivizes the weatherman to tell the truth, for instance, right? So if the weatherman really believes there's a 40% chance of rain today, how should you reward their predictions or their mistakes in a way that really causes them to report 40% versus doing something like, saying like, well, 40% is below 50%, so I'm just going to predict that it won't rain, and kind of thresholding around a half.
We live in an age now when computers, at least compared to what I grew up with, have gotten insanely fast. We've made a lot of progress in parallelization, specifically in ML and other areas. I think maybe someone a little bit cynical could look at different learning problems and say, why do I care if it's efficiently learnable or if it's learnable in polynomial time? Can't I just compute my model offline in some very inefficient manner, and then once I've got it, I can run with it, deploy it to some production system? What are your thoughts about kind of that point of view, that maybe efficiency of learning isn't a critical thing to be considering?
Well, I can certainly understand the point of view of practitioners that perhaps complexity theory has limited impact on the daily practice of machine learning. I'm not unsympathetic to that view. I still think it's extraordinarily valuable to understand what the computational limits on learning are. I don't think, even as a practical matter, given the scale of machine learning problems that many large corporations, for instance, tackle today, that ignoring, whether you need a theorem or not to think about it is one thing, but the idea of ignoring efficiency considerations because of the power of kind of modern CPUs, I think is not true, right? The amounts of data processed by, companies like Google and Facebook on a minutely basis are such that ignoring complexity theory entirely, if they just want to train the models they want to train in the time that they want to train them, they need to think carefully about efficiency. And they may not do that using complexity theory, but you can be quite certain that they're thinking very carefully about how to optimize computations, how to distribute them over CPUs, how to stream, the right amounts of data in a distributed fashion, how to deal with the communication overhead of distributed computation. Very, very smart engineers think very carefully about these issues. In some ways, I think the right way of answering your question is to kind of turn it on its head, which is rather than thinking that the power of modern CPUs lets us ignore complexity considerations, if you like, I think most practitioners would think like, well, what can we now solve by being clever that we couldn't have solved before we had these CPUs? So it's not so much as like, oh, now we've got cycles to waste. It's now we've got cycles to tackle problems that we couldn't have even dreamed of even a decade or two ago. But still, even with the advances in computation and parallelization that you mentioned, to tackle the largest problems that are out there today, you still have to think very carefully about how you set up the optimization.
And there's a lot we can get into about, the limits of what's learnable. And I think it maybe gets technical very quickly, but if you were to kind of sum up the way practitioners consider the limits of learnability, are there some key theorems or key heuristics we can take away to say about, what problems probably are efficiently learnable or how to recognize one when we see it?
Maybe one thing that's worth saying that is sort of slightly more towards the theoretical side, and I'll full disclosure admit that I was involved in this work, which happened a few decades ago now. When one thinks about why can't we just learn anything we want to learn, right? Why can't we learn arbitrarily complicated functions or models? One useful thing to notice is that there are other very useful computational artifacts that influence our daily lives that are predicated on certain learning problems actually being hard. So public key cryptography is an example. So if you think about cryptography at a high level, modern cryptography is based on the premise, and I don't mean this in principle, I mean in practice, it is based on the premise that there are certain functions that are easy to compute but are hard to learn. So when you and I exchange encrypted emails, for instance, we want the encryption part to be easy. We want it to be efficiently computable. We don't want, if I've got a few pages of text and an attachment that I want to send to you and we need to encrypt that, we don't want that to take 15 years of CPU time. On the other hand, we don't want a third party who's kind of viewing the traffic back and forth between you and I in an encrypted fashion to be able, from a small number of examples of that encrypted traffic, to break the encryption. Really kind of baked into cryptography is the idea that there's some class of functions which is efficiently computable on the one hand, but very, very hard to learn. One can actually make this technical. One can point to, some natural learning problems or classes of learning problems that you might plausibly want to solve or learn and show that actually learning those classes of functions or models would imply that, for instance, the RSA crypto system, which underlies the HTTPS protocol, would be broken. I don't think anybody right now, from a practical standpoint, is on a daily basis trying to learn functions of that complexity. But it kind of shows you that at the outer limit, it's not just that we are seeking to get the predictive benefits of machine learning, we're also basically counting on there being limits to that predictive benefit because we need hard learning problems specifically for cryptography to be possible.
So one of the areas I've never personally worked in, even though I know you have a deep amount of experience in doing work in, is finance. What's interesting to me about the stock market and things like that is I know if I go and grab some stock data and I build myself a little model and it appears to predict really well, I've overfit in some way. It can't be that some trivial thing I come up with is useful in predicting. Someone else would have already found that and exploited it and the market would have adjusted. So in some sense, one could cynically look at trying to predict something from the market and say most of the features, most of the input data is just white noise. There's nothing much learnable here because if there were, someone would find and extract that signal. Do you agree with that point of view of looking at it, or is it that the market as a system is so complex that it's something learners are unlikely to be able to find the underlying mechanism of?
Let's see. So first of all, I definitely agree with the sentiment that financial markets are a domain where the pitfalls for machine learning are far more numerous and toxic than they are in other domains. And that for that reason, I kind of share your skepticism, although I'm definitely of the never say never attitude. But in general, I do think it's the case that the idea that you can just get market data, for instance, that's available to any civilian and run generic learning algorithms on it and find something that beats the market, quote unquote, is extremely unlikely. Part of it's for the reason that you say that, somebody else would have found it and, arbitraged it away. But I think part of it is that, markets involve strategic interaction. And these days they involve strategic interaction between algorithms operating at very, very high speed. That strategic interaction is very different than a lot of the success stories you hear about machine learning, which are often operating in what is often either a stationary environment, one that's not changing much, or at least that is changing in ways that aren't directly influenced by your own, actions. So to, put this in plain English, if I'm trying to build a model predicting whether images have a cat in them or not. As hard as that problem might be, at least I can be reasonably certain that the nature of cats in images doesn't change in response to my mere effort to predict it, right?
Mm-hmm.
So, cats don't morph their physical properties because I'm trying to write a machine learning algorithm to predict cats in images. Whereas that's kind of what it's like in finance. Your very effort to make predictions and act on those predictions causes impact in the markets that's almost always adverse to the prediction that you're trying to make. And, market impact, as they say in quantitative finance, is one source of that, but it's not the only one these days. I think there's actual strategic and gaming behavior going on in markets where algorithms are either being directly designed or are learning from data to detect patterns of behavior by other market participants. It's almost as if prediction in financial markets is something like a zero-sum game, whereas it's just not true of, we can all predict cats in images successfully, and none of us kind of cannibalizes any one of the other of us' success. Whereas this is very untrue in financial markets. And so it makes things much, much harder and more difficult, although that doesn't mean there aren't a lot of us still working hard on trying to do exactly that.
One of the ways I'm looking at that then, especially when you point out how responsive, how multi-agent and adversarial the market can be, it's probably a lot of the, modeling something in an agent participating in that is p-space or possibly much worse. Is that really why it becomes, is that an interesting point of complexity when talking about trying to model the market? That the actual thing you're trying to operate, we know has a known complexity that's probably inefficient?
I guess I haven't really thought about, financial markets seem, again, even though there is very interesting complexity theoretic work on multi-agent systems and game theory in particular, in the same way that, traveling salesman is believed to be a hard computational problem in the complexity theoretic sense. So are computing different types of game theoretic equilibria, like Nash equilibria in multiplayer games. But I don't even know how to start to apply that kind of thinking to financial markets, just because, complexity theory, whatever complexity class you're talking about, starts with well-defined inputs and outputs, right? It's like, I've got a graph and I want to compute all shortest paths, or I've got a graph and I want to compute the shortest tour, right? Or I've got a game with payoffs clearly described as my input and I want to compute a Nash equilibrium. Whereas financial markets are really like a perpetually running dynamical system where there's no clearly defined input and no clearly defined output. I'm not saying there aren't sub-problems in that aren't interesting to think about, but it's extremely hard to sort of figure out how to map the language of complexity theory onto something which is perpetually evolving and changing and adapting and in a strategic way, the way financial markets are. Not saying it's not an interesting thing to think about, but I think there's kind of a conceptual gap at the very beginning there.
Yeah, I see what you mean. So one distinction, we've kind of danced around the concept, but I was wondering if I could ask you for the formal definition that I appreciated from your book. It's the distinction between sample complexity and computational complexity. Okay, data skeptic listeners, I want to tell you about the Mendoza College of Business at the University of Notre Dame. They have a program where you can earn a Master's of Science in Business Analytics degree in just 12 months. You can do this while you're still a working professional. It fits your schedule as long as you can attend classes in downtown Chicago on Fridays and Saturdays. That'd be a real treat. I love the downtown of my hometown. You'll learn from in-person Notre Dame faculty and interact with experienced classmates from a variety of industries and cities across the U.S. While building your network, you'll also have a dedicated career coach to help answer those questions you don't know who exactly to ask about reaching your professional goals. Grab a pen or open a new tab for the URL I'm going to give you. It's Mendoza, that's mendoza.nd.edu/dataskeptics. At their site, you can arrange a Chicago campus visit to learn more about the Master of Science in Business Analytics program, and most importantly, you can get a code to have your application fee waived. Visit mendoza.nd.edu/dataskeptics or email msba.business@nd.edu. It's the distinction between sample complexity and computational complexity.
Yeah, so this is a distinction that we were alluding to earlier in the conversation, which is let's use my running example of predicting whether there's a cat in a digital image or not.
Mm-hmm.
And so here the data consists of images of cats, and since it's a learning problem, we usually hope to solve this problem using supervised learning methods, i.e., I have a bunch of images, and they've already been labeled, let's say, by a human as to whether there's a cat in the image or not. So this is kind of my training data. What I want to do with that data is to take these images along with labels indicating for each whether there's a cat in it or not. The kind of computational problem is to fit a model just to that data. So I have 1,000 images, and let's say 500 of them have a cats in them and 500 don't. I want to find a model which somehow, by using properties of the image of these 1,000 images, will learn a model that kind of separates the cats from the non-cats, if you like. Okay? And this is a purely computational problem that kind of falls well within the language of computational complexity. The input is these 1,000 labeled images. I have to pick some class of models, let's say neural networks or decision trees, and I have to represent the images by some features. I could just use the raw pixel color values, but that's probably not a very sensible representation. So I might want to do things like pre-process the images by running edge detection algorithms, for instance, to sort of find out where the edges are. But whatever I do in this direction, the core problem is pretty easy. I want to find a model which on these 1,000 images correctly or approximately correctly predicts which have cats in them or not. That's the computational problem. But that's not really the problem I care about at the end of the day. What I then want to do is then apply that model to new images that I've never seen before and have it correctly predict whether there's a cat in the image or not. And so computational complexity refers to how difficult the optimization over these 1,000 sample images is. And sample complexity refers to the question, well, if I had 1,000 data points in my training set, what kind of error would I expect on new images that I'd never seen before? That's really more of a statistical question, right? It's like when do I have enough data relative to the complexity of detecting cats and the complexity of the model I chose to fit to these 1,000 images? When do I have enough data, for instance, to claim that if I perfectly classify these 1,000 images, that I will have only 7% error in predicting cats versus non-cats on future images?
I guess in terms of sample complexity, do you feel that that is an area that we have all the tools for, or is this an area that we're going to continue to see more advancements come out and be able to say the right ways of looking at models or measuring one from the other, especially as we're getting into these areas where more and more of machine learning is automated, especially like deep learning, where we don't always know exactly what it's doing in the hidden layers?
First of all, this general topic of sample complexity and how do you, as they say, regularize your models so that you're balancing the complexity with the goodness of fit to the 1,000 training images. This is a very, very active area of research to this day. My own opinion is that we've kind of gotten to the point where the empirical approaches to these methods that are being used in practice that seem to work very well, it's hard to come to a very refined, detailed theoretical understanding of why they work so well. And that's probably because why they're working so well doesn't just have to do with kind of the math of the algorithms. A big component is probably the specific data sets on which they seem to work well, right? Mm-hmm. And what I mean by that is that what's a good way of regularizing complexity on the problem of detecting cats in digital images might be a bit different than the details of the optimal way of regularizing complexity on some other prediction problem. In general, the more you find yourself in a world where what works well depends on the details of specific data sets, the harder it is to come up with satisfying theoretical explanations of success. In theory, we try to prove things, and in general, proving things is a big constraint, right? I mean, there are many more things that are true or that work than you're going to be able to prove are true or that work. And so I do think we're at the point where, in many ways, the advances in this topic are being driven by applied work. and that's kind of as it should be. And in general, while we have a lot of understanding about our algorithms in machine learning, we often apply them to very, very large, complex data sets these days that we don't really understand that much about. And so when the success or failure of a particular method is some kind of mixture of the properties of the algorithm and the properties of the data set, theoretical understanding can be hard to come by.
I'm glad you had touched on earlier some of the overlap with game theory. I've enjoyed a number of your lectures I've seen on YouTube. We'll put a few in the show notes where this topic comes up. In my own survey, I've found it's pretty easy to find proofs and papers and interesting work where someone shows that an equilibrium exists, but it's inefficient to compute it. And this has always been a little bit of a point of frustration for me because I'm thinking, how are these agents ever going to fall into this equilibrium or elect to choose it if they couldn't possibly have computed it? Am I being too cynical? Is there something I'm missing when I wonder about results where there are equilibria but they're, infeasible to compute?
No, I don't think your frustration or mystification over that kind of thing is unwarranted. There's a couple things to say here, I think. One is, and perhaps this has come up in your previous podcasts on complexity, the vast majority of work in complexity is kind of worst case analysis. Mm-hmm. So when somebody says that this or that problem is intractable, they mean that the nastiest instances of this problem are intractable. They don't mean that the typical case or the one that you're going to encounter in practice or the one that actually occurs in the real world is necessarily intractable. And so all of the time, people very effectively and efficiently solve NP-complete problems in practice. And there's no contradiction here. It just means that somehow the instance of the problem that they're encountering is not the worst case one. That being said, I generally do think it's a conceptual and even practical problem for game theory and microeconomics if the equilibrium concept that you're studying is an intractable one, especially if you're really thinking about that equilibrium concept in the large, by which I mean, you're thinking about very, very large interactions between a large number of agents or participants. I think in game theory, even more important than there being a fast algorithm, because an algorithm refers to centralized computation. And in things like financial markets, all of the actors are behaving independently in a distributed fashion. The way I might say it is that if you're studying an equilibrium concept that doesn't have not just a good algorithm for computing that equilibrium, but a good learning algorithm, a good distributed learning algorithm, then that's a cause for concern. Maybe the way I would think about this is to turn it on its head and say, if you're studying an equilibrium concept that doesn't have a natural, efficient learning dynamic, then maybe you're studying the wrong notion of equilibrium. There are generalizations of things like Nash equilibria, for instance, that are not only efficiently computable in the complexity theoretic centralized computation sense, but have very efficient distributed algorithms in which, if all of the players in this game play an algorithm of this variety, we will all quickly converge to some notion of equilibrium. To give one concrete example of a type of equilibrium that's received much more attention in recent years and in the computer science community in particular, it's the notion that's called correlated equilibrium, which is a generalization of Nash equilibrium, but that unlike Nash equilibrium has the great virtue that there are very simple learning algorithms that will cause a population of players to converge to a correlated equilibrium.
I'm actually going to see if we can put some links in the show notes as well, because I think it's an important topic that a lot of my listeners won't be deeply familiar with. So one of the points in the wind-up of your book that you were making, and I know it's been published a few years ago, so things have advanced in the field.
Quite a few, yes.
You made a statement about this being sort of almost preliminary in the beginnings of the theory of efficient machine learning. And I know there have been some notable papers that have come out in the intervening years, and people continue to do good research, but I wanted to see if I could kind of get your sense of where the field's at. Is there a lot of low-hanging fruit? Is the importance of complexity and learning coming into its prime possibly as we see deep learning becoming such a prominent fixture in industry? Or where are we at, I guess, in general with the ideas?
needless to say, since we wrote our book, there have been massive advances in machine learning. And we wrote that book at a time where it was very clear that the ground was shifting on a very regular basis. And so it didn't feel like the time to write some definitive, comprehensive, exhaustive treatment of the field. Plus we were lazy and didn't want to write such a book anyway. And so much preferred to just pick kind of a handful of illuminating, interesting topics and treat them in some depth. I'm trained as a theoretical computer scientist and have wandered far and wide in my career, but I think continue to see the world first and foremost through the eyes of somebody trained in algorithms and complexity theory, even though, most of my work is in machine learning and algorithmic game theory and related topics. To me, complexity theory is almost equally or perhaps even more valuable for the way it teaches you to think about the world than it is about the specific results and how applicable they are to exactly what's happening empirically on any given day. As a theoretician, I'll be the first to grant that I think a lot of the massive advances that have happened in machine learning experimentally in the last 5 years or so are, really due to practitioners that kind of developed these ideas as far back as the 80s, just pushing and pushing and pushing on them for many years through times when we didn't have either the data or the CPU power to kind of realize the power of those ideas. And now the world has changed and we do. And so I think credit there goes to the people that were doing that experimental work all this time. So in terms of kind of complexity theory per se coming into its prime in the field of machine learning, I think it's always been a very important component of machine learning. And one of the reasons I love working in machine learning is when I look at theoretical colleagues who work in other areas, I feel very fortunate to have been working in an area of theory where there is not just a very strong experimental community, but a very strong dialogue between theoreticians and practitioners. Mm-hmm. And one can point to many notable instances in which that dialogue really led to important algorithmic practical developments. One that comes to mind is boosting, but I think support vector machines fall into that category as well. So, it's not like the practice of machine learning is full of people who don't care or don't appreciate theory. They might be selective in what they appreciate and what they think is valuable to experimental work. But the traffic between these two sides has always struck me as extraordinarily healthy. And when I look back at my own career, I feel like, wow, even though I didn't go seeking that, I feel really lucky that I kind of ended up working in an area of theory where you can really test your ideas on data and you can really get feedback from experimental people about the, efficacy and usefulness of your ideas. It's not like I think, our day has come. I think machine learning's day has certainly come, and that's very clear. And I would like to think that a lot of the success of the field is due to this kind of continual dialogue between, people that want to prove theorems and think about the world that way, and other people that want to just go out and get better and better performance on large-scale data sets.
Well, maybe to wrap up, we could pivot just slightly to another topic I wanted to touch base with you on, because I've seen a couple of great lectures you've given on the topic, and that's algorithmic fairness. We've talked about it a bit on the show before in the past, so I think people are aware of some of the ideas. Could you share your general thoughts about how are things going to play out in the future? I would imagine there's no stopping algorithms being used in various aspects of our culture. Do we need open source? Do we need, more analysis? Do we need restrictions? What are the impacts socially related to algorithms and fairness?
This is my main current research area, and there are many people in the machine learning community these days who are very carefully and deeply thinking about what it would mean for a machine learning algorithm or model to be fair, as well as adhering to other kinds of social norms like privacy or transparency or accountability and the like. This is a very important area, and it's very important for not just policymakers, but actual, the actual rank and file machine learning research community members to work on. Again, this is one of these topics that people have been thinking about for long before machine learning was a thing. So, statisticians for many decades have thought about when your model is making decisions about individual decisions, let's say in lending and or mortgages, wanting to build models that aren't discriminatory against, some particular subgroup or race sex or gender or what have you. But I think what raises the stakes for all of this is the fact that more and more these days, very large scale and very complicated models are being built that make autonomous algorithmic decisions that are of great consequence to the lives of specific individual citizens, like, criminal sentencing, mortgages, lending, college admissions, employment, etc. This was an issue even when the models you were building were kind of straightforward linear regression models, and you knew that, each variable kind of had an independent effect on the output. That kind of understanding is completely absent in general in something like a deep neural network or even a decision tree, as far as I can tell, if it's a large, complicated one. Mm-hmm. And my own view on this is that because this algorithmic decision-making is happening at scale now and is automated, even though I think regulation and legal and watchdog efforts will continue to play an important role, to put it in computer science terms, they just don't scale. Right? If we're going to try to catch instances of discrimination in all of the forms and complex ways it could take place in learned models, we can't have human beings eyeballing the models or even analyzing their outputs trying to catch all such instances. And so a lot of the current work in this area is really about getting fairness inside of the algorithm and inside of the models itself. In other words, having these algorithms and models be self-regulating and endogenizing, so to speak, the fairness inside of the code of the algorithm. At a high level, this is not conceptually that difficult. The devil's in the details, and there are a lot of details. But in general, right, if you think about a typical learning algorithm minimizing some objective function which has to do with its predictive error, right? You have data and you want to find a model that minimizes the error on the data. If you can just write down a mathematical formulation of what it means for that model to be fair also, then you can add that to your objective function, right? So in the same way as we talked about before, I could try to train a model that balances goodness of fit to the data with the complexity of the model. I could instead choose to balance goodness of fit to the data with how unfair the model is on the data. Fairness will be a constraint. If you give me whatever your favorite definition of fairness is, let's say approximately equal false negative rates across different populations. So, I want a statistical model that it's going to make mistakes, so sometimes it denies credit-worthy people loans. But it should do that the same rate across different racial groups. It shouldn't be that there's some minority group on which the rate of false rejection is much higher than the overall population. So I can write down a constraint like that in a mathematical way and incorporate it into the function that I'm trying to optimize, let's say in a deep learning for neural networks, right? Mm-hmm. Then the question is what's the cost going to be? By which I mean, by trying to balance goodness of fit with fairness, I'm not going to get as accurate a model as I would have if I ignored fairness, right? It's just like simple logic. And so I think the hard thing is still kind of comes back to policy decisions, which is in any given application, how important is fairness? How much unfairness am I willing to sacrifice in order to get higher accuracy and vice versa, right?
Right.
Maybe if it's like, well, I want to make sure that Google is showing, ads to different racial groups at approximately the same rate, maybe I think and only maybe, I might think, well, the stakes there with respect to fairness are a little bit lower than in criminal sentencing. So maybe I'm willing to allow a little bit more unfairness in the ads that are shown in order to get a lot more predictive accuracy. But maybe in criminal sentencing, it's exactly the opposite. I'm like, I don't want to give up on the fairness at all. And if that comes at the cost of a lot of predictive accuracy, then so be it. But no matter what, there's going to be that trade-off. And one of the hardest things talking about this kind of thing to non-quantitative people is just getting them to accept that fact, that you can have a menu of choices here, but you cannot have the best possible accuracy and the best possible fairness simultaneously.
Yeah, that is interesting. In the watchdog approach, it seems to me like you're trying to say out of all the 2 to the n possible models we might have built, can you recognize which ones are fair and which ones aren't, which is kind of a crazy problem. But you've almost restated it. You've baked it into the constraint we're trying to optimize for, that if we can quantify some notions of fairness and these sorts of things, then the optimization does what it does. In that conversation you were mentioning, though, where, getting people to think that way, can you talk a little bit about that process? I can, from my own background, appreciate how difficult that will be, or how hard it can be for someone to think that, it's impossible to eliminate bias. We're just going to minimize it within some epsilon or something like that. Have you had a chance to speak with lawmakers or policymakers? Who's the typical audience that ends up in the discussions?
Both of these. And by the way, just to be clear, these are very sophisticated audiences. I find the easiest way to make the point is to, show them a plot from a real data set in which fairness is a concern. So, some lending data set or some predictive policing or criminal sentencing data set, and, actually run a learning algorithm which is trying to minimize some objective function that's mixing predictive error with unfairness, and run that algorithm many times, changing the relative weight of fairness versus accuracy, and just kind of showing them the so-called efficient frontier that gets traced out, right? So in the same way that it's kind of accepted wisdom on Wall Street that at least on average, there's a trade-off between risk and reward, right? Like if you look at the stocks that historically have the highest return, they also are more volatile. And so it's the same kind of thing here. There's some kind of frontier, if you like, that you can't beat, right? You can do worse than that frontier, but the best you can hope to is to be on it. And, in these plots, if I could show one of them to you, one axis would be kind of how accurate the model is, and the other would be how unfair the model is. And there'd be a curve in this two-dimensional plot, and at one end of the curve would be the model that has the highest predictive accuracy but entirely ignored fairness, and that will get some error. And at the other end of the curve is a model with higher error that's perfectly fair. And in between, you get things in between. And so I find that the best way of making this point is to show a plot like that and say, look, these are your choices. You can tell me that accuracy is the most important thing, and I will point you to the point on this plot, and you can tell me whether you like how unfair you're being in this model to some subpopulation, some racial group, for instance, right? Yeah. And so sometimes, you get resistance and say, oh, no, there's got to be another way. And, they say like, well, what if we change the class of models entirely? And I'm like, okay, you could do that. And there's going to be some different curve for that class of models. Right. And there will be trade-offs there as well. In some ways, I think one of the good things that's coming out of this work on studying kind of algorithmic fairness is it's just forcing one to be precise about what you mean by fairness in a way that you didn't really have to when you weren't like implementing it in an algorithm that was going to make decisions about actual people. We also have to remember that it's not like these trade-offs didn't exist before there were computers. All the time, judges making sentencing decisions, however they think about it, implicitly or explicitly, they're making some trade-off between letting innocent people go and convicting innocent people. On the one hand, you can say like, well, all we care about is being accurate as often as we can, but maybe being accurate as often as you can involves actually discriminating against a subgroup. I'm perhaps overstating things, but I do think from my fledgling wanderings in other literatures on fairness that the fact that human beings were making these decisions and that you weren't actually thinking about committing to a definition and writing it in a computer program kind of, let one debate these things in a more philosophical way than one has to in the context of machine learning. On the one hand, I do think that the widespread use of machine learning is perhaps exacerbating certain kinds of unfairness. But on the other hand, it's making us think more scientifically about the issue than we ever have before.
Absolutely. Yeah, I love the way you framed it, because now it's parameterized. It's no longer some soft discussion. We can have a rigorous numeric discussion about, how do we measure fairness in a system and how do we explore those trade-offs. I really like that.
Yeah, and some people, by the way, I'm sympathetic to the people that object to that formalization and algorithmization, if you like, as kind of, oh, you're somehow taking something that is the domain of kind of human morality and putting it into machines. And just to be clear, I and my colleagues are not proposing that. We're not proposing that computers decide what fairness means. We're saying humans need to decide what they mean by fairness and commit to precise definitions. The other thing we need to remember is that when people say, oh, I don't like the trade-off that you're proposing to me, we have to remember that these trade-offs were present before algorithms were making these decisions as well. There was sort of nothing we could do about them. I think it's important to remember that the initial baseline for algorithmic fairness shouldn't be perfect fairness, but being at least as fair or better than human decision-making.
Yeah, absolutely. Well, I like it also because there's, I think, room then for someone to raise criticism if they were so inclined and say, you picked the wrong subgroup, so your constraint is somehow flawed, and I want to suggest a new one. And we can have the debate in that context if they feel that somehow it's not reflective of the real idea of whatever fairness means.
I mean, that's a good way of putting it. I mean, I think all of these formalizations that I'm suggesting aren't meant to take agency away from human morality, but they're a language. They're a language in which to talk about different notions of fairness. They're a language in which to talk about what groups you're trying to protect. And I think that introduction of greater mathematical rigor into that conversation and thinking about actually making it algorithmic and kind of having our models be able to police themselves to some extent, along with human oversight, is a healthy thing for society.
Absolutely. Well, Michael, I want to thank you so much for all your time today and coming on and sharing your perspective on such an interesting number of topics. We'll have a link to your homepage in the show notes for anyone who wants to follow up on your research and check out some of your talks and things like that. Let's talk about NIPS 2017 for a minute. The entire conference is sold out, but I've got a ticket. If you do too, let me know. We might have some sort of meetup. I've gone ahead and started a NIPS 2017 channel in the Data Skeptic Slack account. If you're not on Slack, join us there. Perhaps I'll live Slack a few things when I'm at the conference. And if you don't have tickets, but you're in the Long Beach area, hit me up anyways. Perhaps we'll have a meetup surrounding the event or something like that. Okay, listeners, before we wrap, I want to tell you about how visiting brilliant.org is a great way to follow up listening to this episode. I mentioned Dijkstra's algorithm in my interview with Michael Kearns today, and I took for granted that the listeners knew what that was. If you don't, or if you want to brush up on it, you definitely need to head over to brilliant.org/dataskeptics and check out brilliant.org's computer science offerings. If you do know Dijkstra's algorithm, do you also know the other topics around it that are also important? Things like sorting and graphs and dynamic programming. Brilliant.org is a fun, affordable, and effective way to learn, and their computer science fundamentals and algorithms courses are both great ones that I recommend. If you're looking for another recommendation, check out the Math for Quantitative Finance course. I've just started digging into that one myself. As I mentioned in the interview, I've never really delved into quant stuff, and as a result, we haven't covered quantitative finance too much on the show, mainly due to my lack of background in it. That's why I'm glad to be on Brilliant.org. It's my place to level up. There's a great variety of other courses in science, math, and computer science, from calculus to astronomy to neural networks. Brilliant.org is really worth your time to check out, so head over to brilliant.org/dataskeptics.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.